Section 5.4, use medians and altitudes. So our goal is to use medians and altitudes of triangles. First, to start, a median is a segment drawn from a vertex to the midpoint of the opposite side. There are three different medians on any triangle. So say I find the midpoint of the bottom side. I go from the opposite vertex to that midpoint. That's one median on this triangle. Another median I could draw, say I find the midpoint there, and go from, that's another median. There are multiple medians, like I said, you could draw one from each vertex to the opposite side. The centroid is the point of concurrency of the medians. If you look in your book, there's an activity right before section 5.4 that talks about taking a triangular shaped note card, drawing the three medians, and it's actually the balance point. So for any triangle, once you find the centroid, that triangle, contingent on the paper being stiff enough or the material being stiff enough that it's rigid, will balance on that. So if you took a note card or a piece of cardboard or wood or something like that, if you find the centroid, that is actually the balance point that you could hold that triangle with 1 point. You could balance it on the tip of your finger, for example. Alright, so we talked about the point of concurrency is the centroid. So if you wanted to, you could call this the centroid theorem. And it is the concurrency of the medians of a triangle. You got a whole lot going on here in this diagram because you have all three medians drawn. And so the centroid is point G. And the centroid theorem, or the concurrency of medians of a triangle theorem, whichever way you prefer to say it, the distance from the vertex to the centroid is 2/3 the length of the median. So, for example, BG. So we're looking at this median right there. The full length of the median would be BD. The length from the vertex to the centroid, BG, is 2/3 of the entire median. Some other relationships within here. If this is 2/3, how much is left here? 1/3. So an implied part of this is that GD is 1/3 of BD. Lastly, if GD is 1/3 and BG is 2/3, what is the relationship between BG and GD? What is the relationship between 2/3 and 1/3? We would say that GD is half, because 1/3 is half of 2/3, so GD is half of BG. This holds true for all three sets of medians. On your own, I would like you to do this for median CE and AF. We will discuss these in class to make sure you have them all correct. I would like you to do them on your own at this time. All right. I hope you got all of those. Like I said, we will discuss these in class. In triangle ABC, G is the centroid and BG, so this piece right here, is 12. Find GE and BE. So like we just went through, what I do when doing these problems is, like I said, write the relationship. So BG equals 2/3 of BE. So if BG is 12, that means 12 equals 2/3 of BE. How do I solve this? Multiply by the reciprocal. Multiply both sides by 3/2. Those cancel and we get that BE equals 3 times 12 divided by 2 would be 18. So BE is 18. I'm going to solve for GE. So we know that GE equals half of BG. So we know that GE equals half of 12. GE equals 6. Another example says using triangle ABC from above, so using this same diagram, find AG if GD is 3. So we're given that that piece is 3. What is the relationship between AG and GD? GD, so GD equals half of AG. We know GD is 3. And now we need to solve. Again, we multiply by the reciprocal. And 3 times 2 over 1 would be 6. So our answer would be 6 units. You could set this up and say that GD equals 1/3 of AD and AG is 2/3 and try to do all this conversion. But this is, quite frankly, the easiest and most straightforward way to do that. That is it with medians and centroids. Moving on to altitudes. An altitude is the segment from the vertex that is perpendicular to the opposite side. Note here, it is not always inside the triangle. So we have an example. First triangle here. I go and draw this perpendicular. There's my altitude. But if I have some type of an obtuse triangle, like say this one, if I'm drawing it from this point, what happens is I need to extend this side out in order to draw such that I am perpendicular. This is still the altitude. It's still the height, if you will, of that triangle. It's just that the altitude is outside. That's fine. The orthocenter is the point of concurrency of the altitude. The orthocenter theorem, there's no fancy theorem. All it says is that no matter what type of triangle the orthocenter exists. There's no other relationship, so realistically, take it for what it is. It does exist. And as demonstrated here, and also in your book on page 321, it shows where the orthocenter is for different types of triangles. Again, just like doing when we did circumcenter, we are going to do an activity in which we find these for different types of triangles. Alright. Quick review, because area of a triangle is brought up in this section and it can be a little tricky. Formula for area of a triangle. Area equals 1/2 base times height. When you have a right triangle, it's pretty clear. Base, height. Remember that your height is always perpendicular to your base. So on this next triangle, if I draw my altitude, the altitude will be your height, and whatever side your altitude goes to is your base. So here's one example of how that could look. If you have an obtuse triangle, and say they give you the altitude out here, there is your height. Now, what is this perpendicular to? This base. And only the segment of the triangle. That's your base. This extension, the dotted part, is not part of your triangle, so it is not part of your base. So it's only the base of the triangle times your altitude for your height. Now that we have completed the 4 different relations that we're going to talk about with triangles, quick little review. Do you know what each term means? Median. Segment from the vertex to the opposite midpoint. Altitude. Segment from the vertex perpendicular to the opposite side. Perpendicular bisector. Perpendicular through the midpoint of a segment. Angle bisector. Divides an angle into 2 congruent angles.